This is B. Naresh, working as assistant professor in a ECE department. Today's topic is the volt-ampere characteristics of JFET. So, in the last session, we observed the what is the construction and what is the principal operation of JFET. So, the FET means the field effect transistor. Based on the construction, we classify the two types of the FETs. That is, one is junction field effect transistor. Another one is metal oxide semiconductor field effect transistor. In the last session, we observed that what is the construction of JFET and what is the principle of junction field effect transistor. So based on the construction, and again it is divided into two types, means one is NChannel JFET, another one is the P-channel JFET. And we know that in a FET, the conduction depends upon only the majority charge carriers. If we consider the N-channel JFET, the conduction depends upon the electrons. Why? Because of that in N-channel or N-type material, the majority charge carriers are electrons. If we consider the P-channel JFET, the conduction depends upon the holes. Hence, the P-channel JFET contains the majority charge carriers are holes. Now, today we are going to discuss what are the characteristics in terms of voltage and the current of particular junction field effect transistor. So, if you want to plot the characteristics or to identify the behavior of the junction field effect transistor, we need to apply some biasing voltage between the drain and the source, as well as we need to apply some biasing voltage between the gate and the source. So hence, with respect to this biasing, we need to identify the behavior of the junction field effect transistor and how this JFET allows the conduction across the drain terminal, or the current is flowing from drain to source with respect to the applied biasing voltage between drain and the source, as well as the gate and the source. And based on this biasing concept, we need to find out the variation of the drain current, the rate of change of drain current with respect to the voltage is applied between the drain and the source, while making the gate and source voltage is constant. And from that, we have the two types of the characteristics, and that is represented as, one is output characteristics, and it is also called as drain characteristics. So one is characteristics is output, or it is also called as drain characteristics. Similarly, the another one is called transfer characteristics. So whatever the FET, either a JFET or a MOSFET, the FET contains only the two types of the characteristics. One is output characteristics, or it is also called as drain characteristics. Another one is transfer characteristics. Now we'll see in detail how to plot the drain characteristics as well as how to plot the transfer characteristics. So coming to you, and based on the construction, so here I'm going to choose a N-channel JFET. Let us consider if it is N-channel JFET, and we need to take a N-type bar. This is called a N bar or N-type channel. One side, a electrode is represented as source. Another end, the electrode is represented as a drain. And opposite two ends, it is doped with heavily materials. Internally, these two are shorted, and that electrode is called as the gate. If it is N-channel semiconductor, here we need that gate is doped with a P-type material, and that is a heavily doped material. To allow the drain current across the drain terminal, Now we need to apply the biasing between the two terminals, that is drain and the source, as well as the gate and the source, means to control the flow of drain current in terms of the biasing voltage between the drain and the source as well as the gate and the source. And based on this n-type n-channel JFET, and the source is made up with, means the source and the drain are made up with n-type material. And based on the principle of this n-channel JFET, the source is always emits the charge carriers to allow the conduction across the field effect transistor. And here we consider as the channel is the n-type, hence the majority charge carriers are electrons. The majority charge carriers are electrons. To repel these charge carriers or to movement the charge carriers from the source to the drain towards the channel, externally we need to apply a biasing voltage between the drain and the source. Hence, the source to repel the charge carrier, hence we need to apply the same force. Hence, the source is biased with the negative pole of the battery with respect to the drain. Hence, the drain is biased with a positive pole and the source is biased with a negative pole. And similarly, based on the principle of the n-channel JFET, to control the flow of drain current, the gate is always reverse biased. Hence, the gate is biased with the negative pole of the battery with respect to the source, and this biasing voltage is represented as a VGG. And the biasing voltage between the drain and the source, it is represented as a VDD. So here, this same structure I'm going to replace with this internal construction is replaced with a n-channel JFET symbolic representation, and this is the symbolic representation of n-channel JFET. It contains the three terminals: drain, where D indicates the drain, S indicates the source, and G indicates the gate. And to identify the behavior, means we need to plot the two types of the characteristics. One is called as the output characteristics, or it is also called as drain characteristics. To observe this drain characteristics, we need to plot the characteristics between drain to source voltage and drain current. Means we need to plot the characteristics voltage versus current, ampere. Volt-ampere means the voltage between the output side, between drain and the source. So this is represented as VDS. Hence, VDS versus the output current is the drain current, hence ID. So in this case, we are plotting the characteristics between drain to source voltage and drain current while maintaining VGEG or VGS is constant. By making VGG or VGS is constant. So this is nothing but this type of the behavior belongs to either output characteristics or a drain characteristics. Similarly, if you want to observe a transfer characteristics, the transfer characteristics are drawn with respect to the drain current and along with the gate to source voltage. Hence, VGS means the gate to source voltage versus drain current by making your VDD or VDS is constant. VDD or VDS is constant. If you observe these two characteristics, the drain current is controlled with respect to the applied biasing voltage between the drain and the source as well as the gate and the source. Hence, this type of the transistor is called as the field effect transistor. So, in this case, the field means how much energy we applied between the drain and the source as well as the gate and the source to allow the current or to limit the flow of drain current. Hence, the ID is a drain current is a functioning of the two biasing voltages VDS as well as the VGS. Means the biasing voltage between drain and the source as well as the biasing voltage between the gate and the source. These two parameters are controls the flow of drain current, hence it is called as the field effect transistor. So based on this, now we are going to observe the characteristics of JFET with respect to these two parameters. That is, one is output characteristics or a drain, another one is a transfer characteristics. Now coming to the characteristics. So here, the first case, what I am doing, I assume that the gate to source voltage is a 0 and drain to source voltage is 0. Let us consider a N-channel JFET. I am going to consider this is N-channel JFET. Means the channel type is the N-type material. It is also called N-bar semiconductor or silicon. One end is the electrode is represented as the source. Another end, the electrode is represented as drain. And opposite two ends is doped with a heavily doped material. This is P plus. Then internally these two are shorted. Externally one electrode is connected, that is called as gate. For this case, now I am going to apply the biasing voltage between the gate and the source VGS, that is means the biasing voltage between gate and the source, that is equal to 0, means these two are shorted. That indication is VGS is 0. And similarly, the biasing voltage between the drain and the source is also 0. Hence, between drain and the source, the biasing voltage between the drain and source, that is shorted, means the voltage across the short circuit path is represented as 0. From that representation, here I considered as the drain to source voltage and the gate to source voltage is 0. Means that we are not applying any force between the drain and the source as well as the gate and the source. Due to this, it forms a depletion layer, internal depletion layers between the between the junctions P and N junction. Let us assume that a small depletion width due to this 0 voltage, a small depletion width is a form between this P and junctions. And another point, when the drain to source voltage is a 0, means due to this 0 force, there is no movement of the charge carriers from the source terminal to the drain terminal to form the conduction in a JFET. Hence, at this point, the state is represented as non-conducting state. So why? Because of that, we are not applying any force between the gate and the source as well as the drain and the source. Hence, none of the charge carriers are repelling from the source terminal to the drain terminal to allow the conduction in N-channel JFET. So from that, I represented this internal structure. What happens when the VGS is a 0 and the VDS is a 0. Similarly, for the same point, when I consider the VGS is 0, now I'm going to change the drain to source voltage. Now let us consider it again. For this N-channel JFET, Again, I consider the N-channel JFET. So hence this is N-type bar, and one electrode is represented as the source, one electrode is represented as drain, and opposite ends it is doped with the heavily doped material. Then, so we assume that VGS is a 0, means the gate and the source, it is represented as the VGS is 0, but a biasing voltage is increased from the 0, a small biasing voltage. So we are increasing from the 0, that is VDS is increased from 0. Due to this, a small increasing of biasing voltage between the drain and the source, due to this applied negative energy across the source side, and here the source is made up with N-type, hence the majority charge carriers are electrons. And we know that the electron is a negative charge particle. And due to this negative force, this negative charge particle is repelling towards the positive pole. Hence, electrons are repelling from the source drain with an amount of area as well as the channel length and based on the resistivity of the point. Hence, the drain current, so due to this applied biasing voltage, the drain current is represented, depends upon some parameters, and that is the number of majority charge carriers, how many charge carriers are available in a source, and based on the channel and the conductivity of the channel, it defines the flow of drain current. Another one is the length of the channel. So means to allow this a conduction across the N-channel JFET, we need to diffuse the charge carriers from the source place to drain place through the region is the channel region. Hence, we need to consider the length of the channel also. Then another one is the cross-sectional area of the channel. So these 3 points are affected to allow the drain current from the drain terminal to the source terminal. So from that, it is represented as the resistivity of the channel or resistance of the channel is represented as rho L by A, where L is the length of the channel, A is the cross-sectional of area, and this is rho is the permittivity of the channel. Hence, from that, I am going to define the drain to source voltage. So, in generally, we know that the drain to source voltage V means I into R. R. If you want to define this drain current, ID is represented as VDS by R. Hence, the drain current is represented as VDS by R. Now, you can substitute this R. So, hence it becomes VDS by R means rho L by A. Hence, VDS into A by rho L. And from this point, the drain current is directly proportional to the applied biasing voltage between the drain and the source as well as the cross-sectional area of the channel. And the drain current is inversely proportional to the length of the channel. So these are the parameters affected to allow the drain current with respect to the applied biasing voltage. Hence, let us consider, I am going to draw this characteristics of a JFET, and this is the drain characteristics or a output characteristics. If you want to plot this drain characteristics, means the VDS, the drain to source biasing voltage versus the drain current by making VGS or gate to source voltage is constant. Let us consider the x-axis is represented as drain to source by voltage and the y-axis is represented as a drain current. Let us consider for this a N-channel JFET, and this is the n-type bar. Source is a biased with a negative, and drain is a biased with a positive pole. And let's take this is a heavily doped material. Internally these two are shorted, externally gay. Let us assume if a VGS is a 0 and this is the VDD, the biasing voltage between this drain and the source is represented as VDS. If a VDD is increases, due to this applied electric field between the drain and the source, the movement of the charge carriers are repelling from the source terminal to drain and to reach the positive pole of the battery. Hence, a conventional current is a flows from the drain terminal to source terminal. So if goes on increasing this voltage, it means already we discussed this. The drain current is directly proportional to VDS. Means if a small amount of the biasing voltage is applied between the drain and source, the drain current is also becomes the minimum. If a large biasing voltage is applied between the drain and the source, hence it allows the maximum drain current. Hence, so when VDS is a 0, if a VDS is a 0, and we know that the ID is also 0. Due to this relation, already we observe this relation. If a VDS is increases, ID is also increases. Hence, if a VDS is increases, the drain current is also increases linearly. And when if apply the maximum voltage means the maximum current, the drain current is a depends upon the number of majority charge carriers as well as the conductivity of the channel and as well as the cross-sectional area of the channel. And due to this a large amount of biasing voltage, if I get a very large voltage, what happens? The drain current becomes maximum. And that state, here it is called as saturated. That state means when at which voltage the drain current becomes saturated or it becomes constant, and that voltage at that point it is called as a pinch of voltage. At this point, that voltage, at which voltage the drain current becomes saturated, that is called as the pinch. Means even though if when the current is becomes saturated, even though if it goes on changing the biasing voltage between the drain and the source, the current becomes constant. Hence, I drawn this is current becomes constant. So it goes on increasing, even though the current becomes a constant, if it goes on increasing at particular voltage, it breaks down the material properties. Hence, the region is called as the breakdown region. And from these characteristics, here we define some regions, and the region is called, one is the ohmic region, another one is the saturation region, and another one is a breakdown region, and a pinch of voltage. So in a ohmic region means when if a VDS is increases, then the drain current is increases, means the drain current is directly proportional to VDS, and here this shows that a linear characteristics, and this one satisfies the a linear characteristics. Hence, that particular region is called as the ohmic region. So, in which region the FET satisfies the linear characteristics, and that region here it is called as the ohmic region. And whenever the drain current becomes saturated or a constant at particular biasing voltage between the drain and the source, and that voltage it is called as the pinch of voltage. And the saturation region means, so if it goes on changing the biasing voltage or the drain current becomes maximum if applied with respect to the applied biasing voltage between the drain and the source, and that maximum current state is called as the saturation region. So hence, from these characteristics, we identified this knee point. So the knee point exhibits the characteristics where the variation of the drain current with respect to the drain source voltage means that is a linear characteristics. So means ID is proportional to VDS. A linearly drain current is the changes with respect to the change in the biasing voltage between the drain and the source. So this point, up to this point, the JFET satisfy the region. The region is called as a linear region, or it is also called as the ohmic region. So that is channel ohmic region. And similarly, the pinch off point means, what is the pinch off point? So at this point, the drain current becomes constant, means it's not changes. So it becomes saturated even though if you are changing the drain or if you are increasing the drain to source voltage. So that is a reason. At which voltage or at which point the drain current is not changing from your maximum value to another value while increasing the biasing voltage between the drain and the source. That point is called as a pinch off point. At that point, it satisfies some voltage. That particular voltage, it is represented as pinch off voltage. And another one is drain to source saturation current. So at this point, the drain current becomes constant or completely enters into a saturation state. So these are some terminologies while representing the characteristics of the JFET or the regions. One is a linear region, or it is also called the ohmic region, and a pinch off point or a pinch off voltage, and a saturation region. Another one is a breakdown region. Now we'll see what happens while changing the gate to source voltage by applying the drain to source voltage. Hence, we are going to find out the drain characteristics of N-channel JFET. So if you want to plot the drain characteristics, means we need to plot the characteristics between drain to source voltage and drain current by making the gate to source voltage is constant with a variable gate to source voltages. So we'll see what happens when the gate voltages or changes with respect to the biasing voltage. So from this case, let us consider in the first case, I am going to take VGS is a 0 and the VDS is increases. So means at this point, let us consider this is source and a drain. Drain is a biased with positive pole of the battery, and the source is a biased with negative pole of the battery. And this is P plus, and internally these two are shorted. And this is VGS is 0. We know that when a VGS is a 0, due to this maximum voltage or VDD or a VDS, it allows the maximum drain current. Hence, ID is directly proportional to VDS. But here VGS is represented as a 0. Hence, if I am drawing the characteristics, let's take, and this is the VDS, x-axis is represented VDS, y-axis is represented as the drain current. So due to when VDS is 0, drain current is a 0. If VDS is increases, ID is also increases. At particular point or a pinch off point, the drain current becomes saturated, hence the drain current becomes constant. Let us assume that this is the case when VGS is 0. Now for this case, in the second case, I am going to decrease VGS from the 0 volt. Means a small reverse voltage is applied. VGS is decreased from 0 means a small reverse voltage is applied between gate and the source. Hence, for the same construction, let us take this is normal construction, N channel, and this is a heavily doped material P plus, drain, and this is source. Drain is a bias with a positive, and the source is biased with a negative. So here now I'm going to apply a small reverse voltage between the gate and the source ends. So VGS is decreased from the zero. Now we'll see what happens with the same amount of applied biasing voltage with a VDD, or the biasing voltage between drain and the source. Due to this reverse voltage, now what happens is that this is the p-type material and internally this is n-type silicon. Due to this reverse voltage is passing through the p-type material, this particular junction becomes reverse bias. Hence, the depletion regions are increases. Let us consider the depletion widths are increases like this. So now what happens? Due to this increasing of the depletion widths, the movement of the charge carriers from the source to drain flow rate is decreases. Hence, the drain current is decreases. So, and that is the reason. When a VGS is decreased from 0, drain current is also decreases. So, hence this is VGS is some decrease from 0. Suppose in a third case, you goes on changing the VGS is a large reverse voltage. Large reverse voltage. If you are up in the large reverse voltage, what happens? This is source and this is drain. Drain is a bias with a positive and the source is biased with a negative. And this is the heavily doped material P plus. Now I am going to apply a reverse voltage between the gate and the source. But here I am going to apply a large reverse voltage. Due to this is a small reverse voltage. This is the case. In the next case, I am going to increase the reverse voltage. Means we know the depletion widths are also increases like this. So hence, if it goes on increasing the reverse voltage, what happens internally? Two depletion widths are increases. Hence, it completely dimensions the channel area. So hence, due to this condition, when the depletion widths are increases by increasing the reverse voltage across the gate and terminal, so what happens? The movement of the charge carriers concentration rate becomes very, very less. Hence, gate current is again, drain current is again reduces. So this is VGS is further reduces here. If it goes on increasing this reverse voltage, what happens internally? It changes the depletion width. At particular reverse voltage, at particular large reverse voltage, it completely occupies the channel. Hence, there is no movement of the charge carriers from the source to drain. If there is no movement of the charge carriers from the source to drain, hence we can say that the drain current is represented as 0. Hence, so at very large reverse voltage, the drain current becomes minimum 0, and that state is nothing but a non-conducting state. So from these representations, here I shown these are the characteristics with respect to the various gate to biasing voltage with respect to the drain to source voltage. So this is already observed. VGS 0, VGS is decreased from 0. Again VGS is further decreases like that. If a VGS is large reverse voltage, then your ID current, drain current becomes 0. So this is the drain characteristics of N-channel JFET. Similarly, now we need to observe the transfer characteristics of the N-channel JFET. If you want to plot this transfer characteristics, the characteristics drawn between VGS versus drain current by making VDS is constant. Hence, and from the construction principle of N-channel JFET, if you want to limit or control the flow of drain current, we identified that the gate voltage should be reverse voltage. Hence, I am going to take the x-axis, means in a negative reverse direction. This is the VGS, that is negative voltage, -1, -2 like that. And the y-axis is represented as drain current. And from this previous analysis, we identify that when with respect to the VDS is a constant, when VGS is 0, what happens when VGS is 0? The drain current becomes maximum. So from these characteristics, when a VGS is 0, drain current, you compare with all these parameters, when VGS is 0 or VGS is small reverse voltage or VGS is large reverse voltage. When VGS is 0, we observe that the drain current is a maximum. Hence, in this point, when VGS is 0, the drain current is a maximum. That current here it is called as IDSS. Means current is a maximum means there is a saturated current. Means drain to source saturation current. Again, if you observe these characteristics, if a VGS is decreasing from the 0, and what happens from these characteristics, drain current is also decreases. Hence, if a VGS is decreasing from the 0, drain current is also decreased from the maximum current. Hence, so slowly it is decreasing. So at very large reverse voltage, what happens if you observe the previous slide? If at very large reverse voltage, it completely occupies the channel. Hence, there is no movement of the charge carriers from the source to drain. At this point, the drain current becomes 0. So that is the reason. So here at this point, the drain current at very large reverse voltage, the drain current becomes 0. So this one shows the transfer characteristics of N-channel JFET. So at this point, so at very large reverse voltage, the drain current becomes a minimum or it enters in the non-conducting state. At this point, the state is called as the non-conducting state, or it is also called as the VGS off state. So from these characteristics, we need to find out some parameters. Hence, we identify the two types of the characteristics. One is drain characteristics, another one is the transfer characteristics. From these two characteristics, we need to identify the important parameters. That is, one is a drain resistance. So this drain resistance is observed from the drain characteristics. Generally, we know that the resistance means it is a ratio of voltage to the current. R is nothing but a V by I. Hence, from the drain characteristics, V means VDS and I means we need to consider ID. Hence, RD is represented as the rate of change of drain to source voltage to the rate of change of drain current. And these drain characteristics are observed by making the constant of VGS. Hence, taken as VGS is a constant. Similarly, another factor, amplification factor, how much amplification is occurs or in terms of voltage gain, it is represented as it is a ratio of output voltage to the input voltage. And from these characteristics, the output voltage is taken as the drain side, hence we taken as a VDS. And input side, that is input voltage is applied between the gate and the source. That amplification factor is represented as a mu. It is defined as the rate of change of drain to source voltage to the rate of change of gate to source voltage by making the drain current is constant. And from this transfer characteristics, so if you observe this transfer characteristics, what we observe from this transfer characteristics, how the drain current is a control with a variation of the applied biasing voltage between the gate and the source. Hence, we need to find out how the drain current is affected with a variation of the biasing voltage between the gate and the source. That is represented as a transconductance, or it is also called as mutual conductance. And here it is represented as GM. Hence, we need to find out the rate of change of drain current with a variation of the rate of change of the biasing voltage between the gate and the source. It is represented as dou ID by dou VGS. By making in this transfer characteristic, we observe the VDS is constant. Hence, at particular point of the drain to source voltage, we identified how the drain current is a control with a variation of gate to source voltage. That is nothing but a transconductance or a mutual conductance. So up to this point in this session, we observed that the volt-ampere characteristics of N-channel JFET, and we also observed that some important characteristics parameters of the JFET. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.